So welcome to WebAssembly in Production, a compiler and a web page. I'm Brian Carroll. Okay, so let's talk about WebAssembly. And first of all, I want to get just a sense of who's here. So how many people have worked in web development in some way, shape, or form? Okay, pretty much everybody. And how many people have heard of WebAssembly before? Getting close to everybody as well. How many people have WebAssembly live in production with a real app? That's about 4 people. Okay, so that's kind of what I expected. So the reason, for anyone who hasn't heard very much about it, the basics are it's a binary code format, runs in the browser, and so JavaScript isn't the only option anymore for running code in a web page. In this talk, I want to get beyond the basics and give you some idea of what it's like to go into production with a WebAssembly app. So we're going to talk about a live production web app that comes from a large code base, and talk about some of the advantages that we got from using WebAssembly and some of the challenges that we ran into. So the context for this is an open source project called Roc, which is a new programming language, and it's fast, friendly, and functional is the tagline we have. So it aims to be faster than the garbage collected languages like Go and Java and C# and so on, but not quite as fast as C and C++ and Rust. A language project is a huge thing, and there's lots of sub-projects within that, and we're going to talk about one of those. And in particular, we're going to focus on the Roc REPL. So a REPL is a tool like this. You've probably seen them before, even if you didn't use that same terminology. So it's just a little tool you type into the command line, and it'll run some code for you as you type it. So it reads the input, evaluates it, prints it, and then loops back around again. And the question that we asked ourselves was, can we port this to WebAssembly? Now, why would we want to do that? Well, one of the reasons is it's really good for newcomers. So somebody who's coming to check out our new language, this is a really good way to do it, right? You don't have to install anything, and it's right there, and you can start playing around with it. Another advantage for us is, as we'll see later, WebAssembly allowed us to make a static site out of this, with no backend. And how is that possible? Well, it's because Roc, the language, one of the things it can compile to is WebAssembly, and the compiler itself is written in Rust, and that also compiles to WebAssembly. So like I said, JavaScript isn't the only option anymore, and lots of different languages are compiling to WebAssembly, and let's see what we can use this for. Okay, so to give you just a better feel for the kind of tools, developer tools we're talking about, I'm going to just actually switch over to a couple of them here. So this is a website called Repl, and they have various different REPLs on their site for different languages. So I can do things like x equals 1, 2, 3, and y equals 1, 1, 1, and then I can go x plus y, and it's 2, 3, 4. Amazing. And so that's evaluating my code as I type it in. And Python is an interpreted language, so it's taking one line at a time and executing it one line at a time. There's another class of languages, like compiled languages, which they're not interpreted, they're compiled. And usually in a language like that, you have a different type of tool on the web. So this is a website called Compiler Explorer, and I'm using the example of the C++ language. C++ is a much more static language, and that means that you've got to actually give it an entire program before it will run anything. You can't just do one line at a time. And what this website is doing is, there's a lot more going on this page, but the main bit is you've got some code in the middle, in the upper panel here, and in the bottom panel, it's printing out the result of that program. So if I change this code here to a different number, you can see the bottom changes at the same time. There was no meaning behind that number. So it changes live as I change the code here, the answer updates. And it's worth having a little look at the developer tools to just see what's actually happening there. So if I change this number again, I can see HTTP request happening. This is going off to some endpoint called compile, which is doing what you would expect it to be doing. So if I change this again and put in another digit there somewhere, it goes off and compiles again. So it's basically grabbing this code as text, sending it off to a server somewhere, and printing the result out again. This is the Roc REPL, which is what this talk is mainly about. So I'll do the same kind of thing in here and use my same example. And it is doing the same sort of stuff. So, but there's a difference, which is, where's the thing? Developer tools. So if I keep the network tab open again, Z is 74, X plus Z, there's no requests. So this is actually all in the front end. And that's something we did with WebAssembly. And I've never actually seen another tool like this use that. So I think this is something we've done that's a little bit new. So let's have a closer look at how these tools work. So the typical architecture you find, and I'm going to use Compiler Explorer as the example, is that you, like I was saying, you have an input panel here, you type in some code, sends that off to a web server, which runs a compiler, and sends the result back through the web server and displays it out here. Some websites, so Compiler Explorer uses HTTP for that. The other one that I demonstrated with Python uses WebSocket. But in our case, one of the reasons we wanted to explore WebAssembly was all of this involves managing servers, and we're just an open source project, and nobody really wants to have a beeper that's going off, because an open source project is something you do as a hobby in your spare time, and mostly that's what we have. So we really didn't want to be doing this. And also, for a language project, you tend to get spikes of traffic, as a lot of people do, I guess. But if there's an article on Hacker News about you, or somebody shares some article, or shares a GOTO talk or something, you can get a spike in your traffic, and then that's bad news. Now you've got to think about, how do I scale my backend and all that stuff. So what we got out of using WebAssembly was we got this architecture where we just served the website from a static file server, so just like a CDN. These are pretty cheap, and they have replication all over the world and everything. You just load the entire front end, and it contains a HTML user interface that we were looking at. It's got an input at the bottom. You type in your code, it sends it to a compiler, which is in WebAssembly, in the same page, so it doesn't have to go out to a server. And the execution output then gets displayed on the web page. And so to build a REPL out of a compiler, so I kind of mentioned briefly earlier the difference between an interpreted and a compiled language. So this type of REPL setup is a little bit easier with interpreters, because line by line is what an interpreter does anyway. For a compiled language, the other system, like Compiler Explorer, where you do the full program, is easier to do, but we really wanted this REPL experience because it's a bit more interactive. And so how you build a REPL out of a compiler is you take all of the input lines of text that have ever been entered in by the user in the current session, you jam them all together, you wrap them up in this main function. So this syntax is probably not too familiar, but it's just indentation means that it's inside the main function. And so we just grab all of those lines, wrap it in a main function, and return this x plus y, which was the thing last line I entered in. So the last line becomes the return value of that function. So we're basically grabbing some strings, sticking them together, and pretending it's a file, because the compiler knows how to take a file and make some code out of it. So we just do that every time you type in a new line. We make a brand new file that is that is one line longer than the last time, and compile it and run it. Okay, so some of the challenges with this. One thing is the download size. It's a 300,000 line of code project. It's quite a lot. The binary size, this binary size is just from my Mac that I'm doing this on, which isn't WebAssembly, but it's just to give you an idea. You don't want a page a web page that's 66 megabytes, it's not going to be a good time. So we're going to need to figure out how we shrink that. That's one of the challenges. And the other challenges are mainly around various WebAssembly limitations that exist. So WebAssembly is not actually able to listen for user input. So that's going to be a problem because we need to type user input in. It can only understand JavaScript numbers. So if we want to listen for user input with JavaScript, that's going to be difficult. It can't modify the web page, and you can't run WebAssembly inside WebAssembly. So I did say that both the language we're compiling and the compiler itself are in WebAssembly, but that's not much good if we can't run WebAssembly inside WebAssembly. So these are the challenges we're going to have to figure out. All right, so the first one, download size. It's way too big. So let's have a look at what is inside this this project. How does it break down? So we'll take the terminal REPL as the example. We saw that at the beginning. And so what it needs to do is receive some input, parse it so that it understands what the text means, all the different syntax, type check it, specialize it, which is just to do with working with generic types, then generate a binary and evaluate it, then turn the result into a string and display it. And so over on the right-hand side of this, I'm showing we've got a big part of the compiler which is for generating production binaries, and it works with WebAssembly and also Intel and ARM style machine code. That uses a library called LLVM, which some people might have heard of, but it's basically a big chunk of code that is there for optimizing and making sure that your final code runs fast. So that's a big piece of the compiler. We've also got these other pieces on the bottom right here for generating development binaries. And we'll talk a bit about why that's different. So these are separate things that we built ourselves, which just basically generate something as fast as it possibly can without worrying too much about optimizations. And so the reason why we structure things that way, we've actually got separate code paths entirely for generating production binaries versus development binaries. And what I'm talking about here is, when you're using a compiler, you've got two different scenarios that you would commonly be in. So the production scenario is where you want to compile your program once, and then you want to run it lots and lots of times, or maybe millions of your customers or something want to run it. So in that sort of situation, fast runtime of the final binary is really what you care about. And if your compile time is really long because you're doing lots of optimizations to try and get that final binary to be fast, that's okay. You're kind of willing to pay a long compile time because it's worth it. You're going to compile it once, but you're going to run it many times. In the development scenario, that's sort of the opposite, because you want to compile it lots and lots of times, because every time you do, you find a bug and you need to fix it and you need to go back and change something and then compile it again and run that. And then you find another bug and you've got to do that again. So what you care about there is the total time, the compile plus run time. And in that scenario, usually people like to run without optimizations, because that gets you the fastest compile times, because all this optimizing takes some time for the compiler to do. And so what we noticed was that this development scenario, we already had the compiler structured with entirely separate code paths for these. And what we noticed was the development side of this is much better for the REPL use case, because you're only going to run the code one time, because the next input line, we're going to have a new program. We're going to compile that again. So the first thing we can do then is use the development code path for the REPL. So we don't really need the production side, and we don't need the Intel output, and we don't need the ARM output. So the way we went about slimming down the page size was to create an alternative entry point into the compiler. When I say entry point, I just mean what you would usually call a main function. So for the standard build of the compiler, it's a command line tool. So you're typing in the name of the file you want to compile and stuff like that, with some options maybe. That's made up of a lot of internal packages. So we have some structure inside of the compiler where it has a bunch of internal packages, which are called crates in Rust. And the entry point is in the CLI package. So that's the one that's interpreting your command line options. And it's the one that imports everything else and sort of glues them together. For the web REPL, what we did was just create a brand new entry point. We just forget about the CLI because there's no command line interface on the web anyway, so there's no need to be interpreting, what minus verbose or whatever. So we just create a new entry point completely and import only the packages, or internal packages and external packages that we actually need for this web REPL scenario. So there's no command line interface, as I said, and none of this optimization stuff, no Intel output or ARM output, just only WebAssembly. And that enabled us to make a kind of size optimized build for this, for the web REPL, by removing all the code we don't need, and we got down all the way to 6 megabytes of uncompressed WebAssembly, and then we can shrink that down again using compression. We use Brotli compression, which is kind of like gzip, but more aggressive. And yeah, we got it down to 2 megabytes, which is a chunky enough web page, but it's acceptable. Yeah, all right. So the next challenges are coming from WebAssembly limitations. When I say Wasm, I mean WebAssembly. It's just an abbreviation. Yeah, so I mentioned these a little bit earlier, just to remind ourselves. It can't listen for user input, only understands numbers, and can't modify the HTML page, and so on. To understand this a bit, to get a better picture for what this restricts you from doing, it's good to understand or to remind ourselves what web APIs are. So web APIs are the JavaScript functions that are built into the browser. They're part of the browser, not really part of the JavaScript language as such. But they're actually what make JavaScript useful in the first place. There's about 120 of these APIs, and WebAssembly can't access any of them, and that's important. So just what do I mean by APIs? Well, it's all of the stuff you've used these. You all put up your hands as web developers, so you've definitely used this stuff. One of the most famous API, web API, is the document object model, the DOM, which lets you insert text into the HTML and listen for user input and stuff like that. So you'll recognize get element by ID probably. There's no equivalent to this in WebAssembly. And similarly for the fetch API, which lets you make HTTP requests and interact with the browser to do that. And again, there's no equivalent to that in WebAssembly. You just can't do it. And this goes on, right? I won't go through them all, but this is me scrolling through the Mozilla documentation for all of the APIs. There's tons of them. And same thing for all of them. There's no WebAssembly equivalent. So the implications of that is that although you can kind of run any language you like in the browser now, it does have to be restricted to basically just data transformations. You take data in one format and you turn it into another format and you spit it out the other side. And if you need to do things like I/O or using anything that's built into the browser, you need JavaScript. So you can have any language you want in the browser, but you also need to have JavaScript working with it in order to access all of this useful stuff. So let's look at how we use those. And before we do, we'll see where do we need them. For this particular project that we're using as our example, where do we need web APIs? Well, we need them for, this is the same diagram I showed earlier on. We need them for receiving the input. We don't really need it for parsing or type checking or specializing. They're all just data transformations or generating WebAssembly. We do need it to evaluate the WebAssembly because all we get out of here is just some bytes and we can't run those. Turning that into a string, we don't need it for that, but we do need it for displaying the output on the screen. Okay. So let's just take that. I'm going to take that diagram and just rearrange it a little bit and show it kind of flowing downwards. I've squished a few of those boxes into one here, compile, because lots of them are just data transformations and we're not going to focus on those anymore. So we need our DOM API at both ends and we need a WebAssembly API in the middle. So yeah, let's start from the beginning and talk about receiving input. which WebAssembly can't do. So if WebAssembly can't do it, then we need to get JavaScript to do it. So we'll receive our input string from the user. Remember, I was typing some code into this web page. We'll receive their input in JavaScript and then call some WebAssembly functions. And then we can do our compile, evaluate, etc., etc. I'm going to explain how all of this works using these kind of box flow diagrams. The ones with the yellow background are JavaScript, and the ones with the darker blue background are WebAssembly. And yeah, things on the left are calling things on the right. So these kind of represent functions or chunks of code. But let's look at some actual code for how that would work. So this is the Roc REPL that I was using earlier on. And some simple JavaScript code to listen for changes on that would be grab the element by its ID and add an event listener. And here's our event listener function on input change. And it's able to grab the text from that input and call this thing called entry point from JS, which is, as the name kind of suggests, is a WebAssembly function, or actually a wrapper around a WebAssembly function that we're calling from JavaScript. There's a to-do here because we need to finish this code off. I'm hiding some bits for later. So one of the limitations that I mentioned earlier was that WebAssembly can only understand JavaScript numbers. It doesn't actually understand JavaScript strings or objects or arrays or anything. But on the last slide, I just said I was passing a string from JavaScript into WebAssembly. So how does that work? Well, first of all, just to get some background, the way that JavaScript and WebAssembly interoperate together is that they use the fact that they build on top of the fact that JavaScript engines use just-in-time compilation for JavaScript. And that means that hot functions, which are just functions that you call a lot, maybe thousands of times, get compiled down inside the browser engine into an optimized form. It's just down to machine code. It takes thousands of calls for a function to be considered warmed up enough for this to happen, but it does happen. And WebAssembly essentially uses that and just bypasses all of that warm-up stuff and compiles straight into this optimized format. So it looks just like a JavaScript function that you've called thousands and thousands of times. So the runtime kind of sees them as the same. And that's how the two can work together. And so to do interop, you can do function calls both ways, but the arguments have to be numbers, and the return value has to be a number if you have a return value. So this is, again, because it's this low-level interface between the two. There is some shared memory, though, between the two. So the the WebAssembly instance has a memory, and JavaScript can see that, and it can write into it. It sees it just as an array of numbers. So you can read it and write into that array of numbers, and it's WebAssembly's memory. So that's how you pass data structures. By the way, that only works one way. The WebAssembly stuff can't see any JavaScript objects or can't look inside them. But JavaScript can look inside WebAssembly's memory. So let's look at an example of what this means for something relatively straightforward, like passing a string, which is what we need to do now, passing a string from JavaScript into WebAssembly. So I mentioned earlier this entry point from JS, and that it was a wrapper around a WebAssembly function. And this is what it looks like. So we're receiving a JavaScript string, and we need to encode that into something that WebAssembly can understand. So we need to, JavaScript has this, one of the many web APIs is text encoder. You can grab a text encoder and pass a string into it, and it'll give you back the bytes that encodes into in UTF-8. Then we're going to allocate some memory space inside of the WebAssembly module, because it needs to make sure that we don't overwrite anything else that's going on inside that memory. So we tell it how many bytes we want. It'll tell us where to put that, what index to put it at in the array. And then we can work out the end index, start index, and the end index, and we set those equal to the bytes that we had. And then we're ready to call the real WebAssembly function. So that's wasm.entryPointFromJS. We can call that with two numbers now, because we've written all the bytes into memory, and now we just need to say where they are. Here's the start, and here's how long it is. Okay, cool. So we got some input. And let's look at how we do the other way. Let's displaying output. Now, we said earlier, WebAssembly can't modify the HTML page. So again, we're going to need to take this display output piece and move it from the WebAssembly side to the JavaScript side. And this is something like how that might look. So here's the onInputChange function that we looked at earlier. We are, again, still just grabbing the input string, the input text from the event, calling our wrapped entry point with the text, getting some text back, and just shoving that into the inner HTML of some output element that we've got on our display area here. And so how do we return a string from WebAssembly to JavaScript? Again, things can only return numbers. And again, we're using this shared memory. So the way that this actually works, in this project I used a code generation tool that we'll talk about again later, Wasm BindGen it's called. And this is how it implements that. So there is a helper function in JavaScript that gets called from WebAssembly with a pointer and a length. So that's like a binary representation of a string. You just got a pointer for where it is and how long it is. We can then grab those bytes based on that pointer and length and decode them. So it's just the exact reverse of what we did earlier. Make a decoder, call decoder decode, and get a string. And the way this works from here is, so this is being called from WebAssembly. It creates that JavaScript string like this, and then inserts it into a global array. That's like actually, they actually call it a heap. Push it in there and get an index from it, because we now have to return back into WebAssembly and back out to JavaScript again, and we can only pass a number. So it seems super complicated, and it kind of is, but this is a general enough mechanism that it lets you create any JavaScript object, and just refer to it using a number as an index. And so our Rust code calls this that helper before it returns back out to JavaScript. So it's this create JavaScript string here at the bottom is what's being called. So this is our entry point from JavaScript that's inside the Rust module. It's taking the input pointer and input length, making a string out of that, compile and evaluate and stringify the input. So that gives us an output. Split that into a pointer and length again. Create the JavaScript string and put it into this global array and get the index back. So it's kind of a lot. So this is how it works to return a string. So and this is it in kind of more pictorial form. So we've stringified the thing. We made a JavaScript in a string in a global array, returned the index back, got it out again, and displayed it. Okay, so that's kind of a lot of hassle, and this is why you use code generation. So this glue code is actually generated by this package I mentioned called Wasm BindGen, which is a Rust specific thing. Other languages have similar sort of stuff. So the handwritten Rust that we actually write does just deal with strings. It takes a string in and returns a string back. There's a link there for Wasm BindGen. So we can use this kind of more simplified model of just working with strings. Okay, so the trickier part is going to be evaluating the user's code. And again, we have a WebAssembly limitation that we need to deal with, which is that we can't actually run WebAssembly from inside other WebAssembly. But that's what we need to do. We need to take this x plus y and somehow run it. So we can take our string, and the compiler will turn it into an array of bytes. Now, normally a compiler would get an array of bytes and just write that into a file, and then that's your compiled binary. But we don't want to write into a file. We don't have a file system. We're in a web page, so we need to evaluate those bytes. But they're not in a format that's runnable right now. And so that evaluate step actually splits into two smaller steps, one of which is called instantiate, and one is run the user code. And so what instantiate means is you take an array of bytes, that's just numbers, and you turn it into an executable WebAssembly instance. And that does require one of these web APIs that I mentioned. And then once we have an executable instance, we can actually run the user code and stringify it and display it. So instantiate is just creating an instance. So this is one of the functions that are built into the browser that you can call. You give it some bytes, which are the WebAssembly binary format. You give it an object with some callback functions in it. So if you want your WebAssembly to call back out to JavaScript, you put them into an object, which lets you give them null names. They have like the keys are strings and the values are functions, so it can call them. So what happens when you do this is it takes those bytes and loads them into the virtual machine in the browser engine, that makes it runnable. So it then turns it into that shared low-level format that we discussed. And what you get back is a WebAssembly instance, which contains WebAssembly functions that you can call from JavaScript. So we're now going to go a little deeper. Right, so this is as far as it goes. But we have created a JavaScript application that calls into some WebAssembly, but that's a compiler, and it's going to need to make more WebAssembly. So we're now going to have to call some JavaScript that makes more WebAssembly. And this is a more clear picture of what that looks like. So there's our top-level JavaScript, receiving the input and displaying the output, calling into the compiler WebAssembly, which does the compiling and stringifying. And within that, it's going to call down again into some JavaScript, and that's going to instantiate and run our user's code. Then we have to create a new WebAssembly module that is the user's code, run it, and pass the answer all the way back. Okay. So if you thought that was bad, we've got to go one more step. This is as complicated as it gets. So just to give you an idea of the kind of things you can run into doing a project like this for real, that is what we're here to talk about. So that callback, I showed that as one callback on the previous slide, but actually it ended up being 3 callbacks. And I'm going to explain why. So first of all, we ran into a minor issue with async. So that instantiate function that I showed earlier on, WebAssembly instantiate, is actually async. And if you've ever worked in any language that has async and await, you've probably found that one of the things that happens is once you make something async, then all its callers become async too, all the way up the call stack. And that's true here too. So this instantiate is async, which means that the Rust function that calls it to compile it also has to be async. And the receiver, event listener at the top level has to be async too. Now, there was some shared code in here that we are actually sharing between the terminal CLI REPL and the web REPL. And we just didn't really want to make that async all the way up, which is what would happen if this run user code and instantiate were stuck together. Then some of this would have to be async too. Now, we could have done that. It just seemed easier to split the function though. so that's what I did. So async interaction between Rust and JavaScript, again, a lot of that is helped by this code generation library, Wasm bindgen, which can tie together Rust futures and JavaScript promises, which are, conceptually the same sort of thing. And then the last complication was when we get the result of running the user's code, we've no way of knowing in advance what size that's going to be. We don't know how many bytes it's going to be. So that means it's tricky to send it back to the compiler without doing an extra step. We need this extra callback to do that. So we had to return back, run the user code, return back with a result that says, here's how big the result is in a number of bytes or kilobytes or whatever. Then reserve that much space, copy the memory from the user code's WebAssembly module to the compiler's WebAssembly module so that it can analyze it and figure out how to turn it into a string, and then display it. And we're done. Okay. So just to summarize what we've looked at. We got a major architecture advantage out of using WebAssembly. We've got no servers to manage, and that means no open source contributors getting beeped in the middle of the night. We reduced the download size to make it fit into a web page in a reasonable sort of size. And to do that, we made a dedicated entry point that's separate from our command line one, and removed the subsystems that we didn't need. And I think we talked in detail about how that worked for our compiler project, but I think the general point of make a dedicated entry point and remove the subsystems you don't need, I think that applies to other projects too. We also talked about how you always need JavaScript. You can't get away without it, even if you're mainly using another language. So for things like HTML input and display, in our case for creating the user code's WebAssembly module, but again, if in your project that might be something else, because there's 118 other APIs that you might need to use in the browser. And we also talked about JavaScript and WebAssembly interop, and how the engine treats WebAssembly a little bit like optimized JavaScript functions. There's a very low-level API between JavaScript and WebAssembly. It's all just numbers and shared memory. And so that means that code generation is your friend for things like strings and async and lots of other stuff. And yeah, I think it's fairly common in a project like this to have to reorganize how your code is structured in order to work around the relatively limited interface between the two worlds. And that's the talk. So there's some links here, the slides will be sent out afterwards. These are some links to the project and some of the source code. And yeah, don't forget to rate the session. Thank you.